All right, so we have a midterm exam on Wednesday. There is no quiz in discussion section tomorrow. And in fact, I think your TA is going to email out and say discussion section is canceled and it's going to be turned into office hours. Okay, so you can go there to ask questions to help you study, ask questions to get help with the homework if you started the homework and things like that. Okay, so no discussion section quiz. And again, to study, look over your discussion section quizzes, look over the old midterm that I posted, and then your lecture notes, okay? And most of the exam will be, here's some code, what's it gonna output, okay? Yeah, question?
Is the regex cheat sheet the only thing that we're going to be given?
Yes, the regex cheat sheet's the only thing as far as like notes and information stuff that you'll be given. Everything else will just be the exam, so yeah. Okay. I will probably tomorrow evening I'll email out a seating chart, okay? And so you'll see that and you'll sit down. It helps with the just the system. I've got a system that I feel like has done a good job in terms of exam organization. So it's just part of that system there. Okay. All right. Today, so it's 6th week, and our class takes a shift. Okay. So the first 5 weeks were all about like R programming, okay, intermediate to advanced R programming stuff. And now we are going to look at some numeric methods. We're going to look at things like root finding methods, optimization methods. We'll do some hypothesis testing later, okay, but hypothesis testing from a computational standpoint. So like in your Stats 10 class or Intro Stats or AP Stats, if you took it in high school, you did hypothesis testing and you did p-values and stuff, but all of those p-values were based off of what? There was a theorem that allowed you to compute your p-values. This is disappointed dad face, okay? Central limit theorem, right? Central limit theorem that allowed you to create your sampling distribution. Okay, well anyway, we'll talk about that. If you don't remember that, you guys are gonna graduate as stats majors. All right, okay. So anyway, all right. I'll reinforce, okay? But anyway, before we get into that, we're gonna use a lot of the computing power of the computer, all right? And it will, we're going to use it to calculate numbers for us. And that's going to help require that we understand floating point numbers, okay? All right. And so here's what we're trying to do, right? So in most of math, we work with real numbers, all right? And so this is like review of whatever, okay? So you guys, I don't know when the term real numbers first introduced. Is that like 9th grade? When are you first introduced to the real numbers? I don't know. Okay, at some point, right? All right, and so how many numbers are there? There's infinitely many, right? Okay, and then so, when you first learn numbers, you learn the natural numbers. You start counting 1, 2, 3, all the way up, right? And you realize there's no end to how high you can count. There's infinitely many numbers you can count to, okay? And then you are introduced to decimals, and then we learn that with the real numbers, there are infinitely many real numbers between any two numbers, right? You pick 0 and 1, and there's infinitely many numbers in between there, and you can't even count them. There's infinitely many, right? This is the real number line, okay. And then, and you learn these rules somewhere, probably like 6th grade, 7th, I don't know, 6th grade, the associative rule and the distributive property and commutative property. And this says things like you can multiply numbers in any order, and it's fine. You can distribute these things, and it works out. You can add A and B first, and it's the same thing. A and B added together first, and then adding C is the same as doing B and C added together, and then adding A later, and stuff like that. Okay, so you have all of this, and these are like central rules that we grow up and have accepted as part of the fabric of life determined by numbers, right? Okay, and then and we represent numbers in decimal representation, right? This, like, I think our understanding of numbers, at least mine, is completely shaped by the decimal representation, in that, like, if somebody asked me to do math with like Roman numerals, like I couldn't do it, right? Like if I would have to like convert it into decimal and then do the math and then come back and convert it back to Roman numerals or something. So, and anyway, if you think about what you have, you've got like this sign, so positive or negative numbers, and then in each value represents a different thing, right? So the number 5,413.29 is, we can think of it as 5 times 10 to the third plus 4 times 10 to the 2, 400, plus 1 times 10, so that's plus 10, plus 3 times 10 to the 0, so 3 times 1, or 3, plus 2 times 10 to the negative 1, so 2 tenths, plus 9 times 10 to the negative 2, 9 100ths, and that gives us 5,413 and 29 hundredths. Right? And then, I don't know, somewhere in like chemistry class or something, they really emphasized scientific notation. Okay, and so scientific notation is kind of the idea that all of these numbers you can just multiply by 10 to some exponent, 10 to some power, and they're all equal, right? And so your standardized scientific notation will take this number 5,413.29 and represent it as 5.41329 times 10 to the third, right? And so the way we got 10 to the third is we took this dot and we moved it over 1, 2, 3 places. We moved it over 3 places, and so it becomes 10 to the third, okay? And so this is scientific notation, and it's very useful because certain numbers are really big, right? So you have Avogadro's number, the number of particles in a mole, and that's like something times 10 to the 23rd. You have like these really small numbers, something along the order of like Planck's constant and stuff, and they're really tiny. And you wouldn't want to have to write this with a whole bunch of, you wouldn't want to have to write the whole number out, right? So you just kind of approximate it and say times 10 to the 23rd, or you do this times 10 to the negative 31. And we're okay with this, right? We're all accustomed to seeing stuff like this. Okay. Pretty much all real numbers have an infinite decimal representation, okay? Especially if you think of numbers like the square root of 2 or pi or e, they're like known to have these numbers that go on forever, okay? Even rational numbers like 1/3, okay? If we wanted to represent it in decimal, we would have to write 3's on to infinity, right? 0.33333 all the way off to infinity, okay? If we wanted a true representation, right? But of course, if we write something down on paper, we can't write 3's off to infinity, so we just write an approximation, okay? And we don't think about this, right? But using an approximation has profound implications for the properties of real numbers that we take for granted, right? So all of those rules that we had earlier, the associative rule, the commutative rule, distributive rule, all of those properties break when you use approximations rather than the actual value themselves, okay? And the reason why we have to use approximations is because computers don't have this semantic understanding of numbers that we do, right? So when we see 1/3 and we turn that into 0.33333, like our brain understands this concept of going off to infinity. Computers don't have that. And so all they get is the 0.333, this finite representation. And we can only have a finite number of digits because we have only finite storage. We don't have infinite storage. So, for example, you buy a computer today and you can buy 8 gigabytes of memory, 16 gigabytes of memory, a terabyte hard drive or something, okay? And let's say you dedicated your entire 1 terabyte of storage to write down the number pi, okay? All the digits of pi. Can you do it? No, you're going to run out. You get a lot of digits. With 1 terabyte of storage, you can store a lot of digits of pi, but you will not get the full number of pi, right? You're going to run out of space because those digits go on to infinity, and it cannot be done, right? And like pi is at least kind of an interesting number. I don't know, people are obsessed with pi, about like getting all the digits of pi. I don't know any other number where someone's like, let's find all the digits of this number. So it just seems silly, right? So if we wanted to represent 1/3, we could dedicate the entire terabyte of storage to represent 1/3. It would just be a whole bunch of 3s, and it still wouldn't do a perfect job because those 3s go off to infinity, right? And so, we say, well, that's a waste of space, right? What did you use you get, whatever, your Google One subscription to store, 100 gigabytes of whatever. What did you use it for? I only tried to represent the number 1/3 perfectly, and it didn't work. So, we're going to just represent numbers with a finite number of space. We say, okay, 64 bits. That seems like a good number of numbers. That's quite a bit. We use 64 bits to represent a number. We're not going to be able to represent numbers perfectly, okay? So we have to approximate a whole bunch of these numbers, right? Okay, so we run into this when you use an old calculator, okay? So here I have a video, right? So here's an old calculator. You might call this an 4-function calculator, even though it's got a square root button there, okay? So when you first used a calculator in grade school, it might have looked something like this. And this calculator can represent 8 decimal values, okay? The screen can hold 8 values decimal, okay? And so I'm going to do 10 divided by 3 times 3, okay? Now what is 10 divided by 3 times 3 equal to? 10, right? What happens when I do it on the calculator? Okay, so this is what happens when you do it on a calculator that only has a finite number of digits, okay? So I go in and I type in 10 divided by 3, and I get 3.33333. I multiply that by 3, and I get 9.999, all right? So here we go. 10 divided by 3, 3.333, and then here, okay. And so I don't get 10 back, I get 9.99999, okay? And we can understand why, right? Because 10 divided by 3 was represented with 3.33333, and then, and it doesn't understand that those 3's go on forever. And so it has those 8 digits, and it multiplies it by 3, and it gives us 9.99999. Okay. So we get that's what we get, all right? Now what if I did the other thing, right? So this is exactly the other thing. If I do 10 times 3 and I divide by 3, what do I get? So 10 times 3 is 30, and I do 30 divided by 3, and I get 10, okay? Okay, so that is not exciting at all, because that's exactly what we expected it to be, right? But the whole reason why I videotaped myself typing numbers into a calculator was to illustrate the fact that this rule, the associative and commutative properties of real numbers, is broken when you try to do calculations on a calculator, okay, or a computer for that matter, right? So 10 divided by 3 times 3 should equal 10 times 3 divided by 3. There's no reason why they shouldn't be equal. But because we are not able to represent 10 divided by 3 perfectly, but only with an approximation, the result is that these two numbers are not the same. One becomes 9.99999, and the other is 10, and those are not the same number. Okay? And so if you are expecting real number behavior, where you can do division and multiplication in any order and get the same number, you will run into problems, right? So you have to, and it's not always easy to predict exactly how things will differ, okay? But you will run into issues where you try, if you are expecting this behavior to be true, you will run into problems, okay? Another scenario here, like if I do square root, I recorded myself taking the square root of 2. So if I do 2 square root, and then I square this number back, okay, we would expect to get 2, but I don't. I get 1.999998, something close to 2, right? I also recorded myself doing 2 squared, which is 4, and taking the square root of 4, and it gives back 2, okay? You can waste 6 seconds of your life and watch that video, okay? But it's going to do that, right? So this is just another thing that shows that when you use a calculator, you don't get back these things, right? Modern calculators today, like if you buy a graphing calculator or a scientific calculator, they've often computed some extra logic in there, so these things come back to be true and equal, but on these older calculators it doesn't happen, right? So you can think of R and the computer inside your thing as being like a powerful calculator, but it still has the same problem where we only have a finite number of digits to represent all the real numbers, which is not possible, right? So look at this, okay? You see this? Let me make my font bigger. Okay, so here A is 0.1, okay? And B, I'm going to do 0.3 divided by 3. And B is 0.1, okay? Now what happens if I do A equal to B? Is A equal to B? Yes? No? Okay, we get back false, all right? And we go, what? A is 0.1, B is 0.1, A equal to B is false. Is A equal to 0.1? Yes, that's true. Is B equal to 0.1? That's false, but what is B? B is 0.1, right? And we're like, what's going on, right? So it feels like, okay, so it comes back false, right? Let's try this, right? So here I'm going to say A is 0.1 plus 0.2. What is that? A is 0.3, okay? Let's do B is 0.3, okay? B is 0.3. Is A equal to B? And it comes back false. And I go, what? Really? Okay. What's A again? 0.3. What's B again? 0.3. Is A equal to B? No, right? What's A? A is 0.3. Is that equal to 0.3? Again, we're coming back false. B is equal to 0.3. That's true. Okay. So these are some of these things that are happening, right? Here I do, let's make a sequence. S is a sequence from 0 to 1, count by 0.1. Okay, so what's S? 0, 0.1, 0.2, 0.3, 0.4. Okay, what's the fourth number in S? That's 0.3. Okay, if I store that as A, S, the fourth number in S is A is 0.3. And if I say B is 0.3 again, B is that, A is 0.3, B is 0.3. We think they should be equal, but again, it's coming back false, right? These are, what's going on here is the same thing where we're expecting 10 divided by 3 times 3 to be the same as 10 times 3 divided by 3, okay? It's the same idea, is that we think they're the same, and in terms of real numbers, they should be, but because the computer's using an approximate, here's just more of this stuff, like I was getting a kick out of this, right? So we just had all these examples, right? 4/5 times 3 times 5/4, right? Should be 3, it is. 4/5 times 3 times 5/4, so this is the associative rule. Also should be 3, it is 3, but if I say are they equal, it comes back false, right? So this 3 is not equal to that 3. What's going on, right? And so we can dig in a little bit deeper and we can say options, digits equal to 20. Okay, and if we do this, what do we get? 0.1 is not actually 0.1. It's 0.10000000001. And what's 0.2? 0.2 is not actually 0.2 exactly, but it's 0.2 something 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 01. Okay, and if I say what is 0.1 plus 0.2, it comes back as 0.30000, and it ends with a 4. And that feels weird, right? This ends with a 1, this ends with a 1. Maybe we can accept that, but then adding these together ends with a 4. That feels odd, to say the least, right? And then meanwhile, 0.3, if I type in 0.3, I get 0.2999999, okay? And so when we ask the computer, is this number equal to this number, it's coming back and it's saying, no, they are not the same. They are not the same, okay? And it's just kind of like asking, is 9.99999 equal to 10? And they're not. There's a difference between them, right? Just another thing. Here is just like a bunch of ways to represent 0.3. I got 0.3, 0.4 minus 0.1, 0.5 minus 0.2, 0.6 minus 0.3, 0.7 minus 0.4, and they all come back as 0.3. But how many are distinct values? It turns out there are 3 distinct values of 0.3 here. I got 0.29999, 0.30004, and then I also have a 0.29993. And you can't tell what you're going to get, right? So I have 0.3 is this, and I can say is 0.3 equal to 0.4 minus 0.1. And that's false, okay? But is it equal to 0.5 minus 0.2? And that comes back true, right? And so how are you supposed to know which one is it going to be true for and which one is it going to be false for? And you can't really predict this, okay? We've got a bunch of these things. And so underneath the hood, what's happening inside the computer is that all of these decimal numbers are being represented in binary, right? So you take a number and you have to represent it in binary, which is going to be in powers of 2. So, 2 to the 0 power is 1s, 2 to the first power is 2s, 2 to the third is, or 2 to the second is 4s, 2 to the third is 8s. And then on the fractional side, you have 2 to the negative 1, so you have the halves place, 2 to the negative 2, which is the quarters, 1/4, 2 to the negative 3, which is 1/8, and you have this, okay? So let me just get into binary, and I think a lot of you guys learned binary, but then a handful of you have not, okay? This for whatever reason in your academic career, just the need to discuss binary has not come up, and so here's just a very, very, very basic primer on binary, okay? So I'll start with this, okay? So here, if we want to represent the number 11 in binary, we're going to represent it like this, okay? So the first thing is the ones place, okay? So 2 to the 0 is 1, okay? And then because it's a base 2 system, each position is 2 to some power. So this is going to be 2 to the first power, so this represents 2. This is 2 to the second power, this represents 4. And this is 2 to the third, it represents 8. Okay, so 1011 represents 18, 0 4s, 1 2, and 1 1. Okay, so 8 plus 0 plus 2 plus 1 becomes 11. All right, if you count in binary, okay, so we can see 11 is 1 0 1 1, and 0 is all zeros, 1 is 0 0 0 1. The 2 becomes 0 0 1 0, 3 becomes 0 0 1 2, and 1 1 makes 3. Here's the 4 place, 0 1 0 0. So we have 1 4. 5 is 1 4 and 1 1 for 5. 6 is 1 4 1 2 and 0 1s, and 7 is 0, 1, 1, 1, 4, 2, and 1 makes 7. Okay, and so on and so forth. We get, this is how to count in binary. Similarly, when you have fractional parts, you have the decimal places, or the binary places, I should say. Okay, so 1/2 is 1 times 2 to the negative 1, and that's represented in binary as 0.1. 1/4 would be represented with 0.01. 1/8 would be represented at 0.001, and 0.375, which is 3/8, is 1/4 and 1/8, 0.011. Okay. And so what's going on is that when we ask the number 0.1 in decimal 0.1, 1/10, to be represented in binary, it actually is this, 0.00011, 0011, 0011, 0011, okay? That part, 0011, repeats on forever and ever and ever, okay? And maybe symbolically, in our head, we can understand this concept of 011 repeating on forever by putting a bar over it, okay? But of course, the computer is not able to go 0011 off forever. And so it has to truncate it at some point, okay? I think it gets 52 bits to represent this, and it has to truncate this at a certain point. And so it's not exactly 0.1, it's a little bit bigger than that. And so, so we get a number slightly different from 0.1, okay? And so when you do 0.1 plus 0.2, these truncated representations are not exactly equal to each other, and we get false back, right? So how do we represent numbers in R, or numbers inside the computer, okay? The numbers inside the computer have been determined by this IEEE 754 standard, okay? This was, IEEE is like the Institute of Electrical something Engineers, and they created this specification in 1985. They made an update in 2008, but the 1985 is all we need to cover because the 2008 completely contains the 1985 specification with just adding a couple features, I guess, to it, okay? You can read all about it on Wikipedia. This standard is implemented at the hardware level on the computer chip itself. Okay, so it's not something that's unique to R. Okay, if you do this on Python, you're going to get the same exact stuff because it's something inherent to the numbers, right? In C, anything that uses a chip that conforms to these specifications. So pretty much everybody, all Apple computers use AMD chips, Intel chips, okay? And pretty much almost all PCs use Intel chips. A few of you might have AMD chips, but they all are conform to this specification. You'd have to go like way back to get older computers that don't conform to this specification, and then the numbers might be represented differently, okay? Anyway, so the way we are going to represent numbers is using binary scientific representation, okay? So if you think about binary scientific representation, you need a significand or a mantissa, and then an exponent, and then we're also going to have a sign, okay? So we're going to have a bit for the sign, for if it's a positive or negative number, and then we're going to have the part that goes 1 point something something something, and that's going to be called the mantissa, times 2 to the something, and that something is going to be the exponent, okay? If you think about the mantissa, okay, this part here, so in scientific notation, when we normalize it, okay, we only have one digit in front of the decimal place, okay? And that digit is not allowed to be 0, okay, right? So the digit in front of the decimal place has to be something between 1 and 9. It can't be a 0. In binary, if you think of a normalized binary representation, that first digit, if it can't be a 0, has to be a 1, because there's only 2 digits. You only have 0 and 1s. Okay, so if it's not a 0, it has to be a 1. So because we're assuming that leading digit's always a 1, we don't have to actually encode it. We'd be like wasting space because it's always going to be assumed to be 1. So the leading digit's always going to be implied to be 1, and that's what we've got, okay? So here's this number, 6.375. If I wanted to represent this in binary, it would look like this, okay? The 6 becomes 1, 1, 0, right? 1 is for the 4, this 1 is for the 2, and 0, 1, so 4 and 2 make 6. 0.375, which is 3/8, is 0 halves, 1 quarter, and 1/8, right? So 1/4 plus 1/8 is 3/8, or 0.375. So 6.375 is 110.011. 420, 0.25 plus 0.125 makes 6.375. Is that okay? Now, if I wanted to make this in normalized binary scientific notation, what would I have to do? I would have to move this decimal place over how many positions? 2 positions, right? I would roll this over 2 positions, and I would have 1.10011, okay? So I'd have 1.10011 times, because I rolled it over 2 positions, I'm going to have to multiply by 2 to the 2. Okay? So if I do that, then this becomes the 1s, the halves, the quarters, the 8ths, the 16ths, and the 32nds place. And I can do all of this calculation, and I would get 1.59375. If I multiply that by 4, I get back 6.375. Okay? So these two things are the same. 1.10011 times 2 to the second. This would be kind of your normalized binary scientific notation. And it has the same digits, we've just rolled the decimal place over, okay? Just like regular old decimal scientific notation where you have the number and you just, to turn it into scientific, you just roll that decimal place over wherever it needs to go, okay? And that determines how many places you moved over, determines your exponent. All right, is this okay? All right, so what we're gonna do is we wanna take something like this and represent it in our computer. And so when we do this, we've got a sign bit, an exponent, and a mantissa. And the computers technically will have 3 different levels of precision. And this is all part of the IEEE 754 specification. You can have single precision numbers, which will use a total of 32 bits for your number. You can have a double precision number, which is 64 bits, or you can have a long double, which will have 80 bits to represent a number, okay? In the double precision, we have 1 for the sign, 11 for the exponent, and 52 for the fraction, okay, or the mantissa, okay? 1 for the sign, 11 for the exponent, 52 bits for the mantissa. And this is why when you type in a decimal number into R, or the default number, and you say type of, it comes back type of double. Okay, it's double. That's where that double comes from. Double precision floating point number. And R really only has double precision floating point numbers allowed for decimal values. Okay, but you could go to Python, you can go to C, and you can ask for single point floating precision, double point floating precision, or long double floating precisions, and things like that. Okay, and each of those things will use different numbers of bits. But as far as R goes, we just have type double, 64 bits here. Okay, and this you can represent a lot of numbers. You can represent about 2 to the 64 power, maybe a little bit less than that, numbers, which is a lot of numbers, but very short of infinity, right? So it's certainly not an infinite number of values. Okay, the 11 bits that we specify for the exponent gives us 2 to the 11, 2048 unique values here, okay? We have 2048 unique values, and we have 2 special cases. If you have all zeros and all ones, they have special meanings, and we'll get into that on Friday, okay? So we have 2046 unique values, and we want to represent both negative and positive numbers, okay? So rather than just saying we're going to have exponents be from 0 to 2046, we're gonna kind of shift all of those down about halfway. And so about half of those numbers will be negative. So we go from negative 1022 up to 1023, okay? And so that means we have an exponent bias of 1023. I'll talk about that in a moment here, okay? And here's just kind of a table showing that. The exponent, if you have all ones, will end up representing infinity or not in numbers, and again, we'll get into this on Friday. And if you have all zeros in the exponent, it's going to be used to represent what we call subnormal or denormalized numbers. And again, we'll get into that on Friday as well. Okay, so to kind of help us understand the floating point representation, instead of having all 64 bits, where we have 11 exponent bits and 52 mantissa bits, we're going to create what's called a mini float. Okay, so a mini float, are going to represent numbers with 8 bits. Okay, and we're going to have 1 bit for the sign, 3 bits for the exponent, 4 bits for the mantissa. Okay, so this will be used to represent the number. So we're going to be able to represent about 64 unique values, actually a little bit less than that. Okay, these will be all the unique values we can do. Okay, so the first bit is going to be our sign bit. If it's a 0, it's going to be a positive number. If the number is negative, the sign bit is 1. Okay, and so one side effect of this is that you have 2 representations of 0. You're going to have a positive 0 and a negative 0. Okay, and I guess that's fine. Okay. All right. And let's think about the exponent. We got 3 bits for the exponent. Okay, that gives us 8 unique exponent values. Okay. And so the binary values go from 000, 001, all the way up to 111. So that gives us decimal values of 0 through 7. But we want to represent negative and positive numbers with this. Okay. And so what I'm going to do is I'm going to take 0 through 7 and I'm going to just shift it down. Okay. And so I'm going to have an exponent bias of 3. I'm going to shift everything down 3 spaces. So the smallest number, 0, becomes negative 3, and the largest number, 7, becomes a 4. Okay? Now, when the engineers were specifying this, they could have picked any arbitrary number. They didn't have to pick negative 3 or shift it halfway down. But they figured, half of the numbers should be negative, half of them should be positive. And they could have chosen negative 4, and we would have gone from negative 4 to positive 3. But I guess they decided to shift it negative 3, so that the positive side would have 1 extra than the negative side. Okay, and so that's what we have. All right, so we have an exponent bias of 3. In general, if you had a different specification, the exponent bias is going to be 2 raised to the n minus 1, n being the number of bits in the exponent. So 2 to the n minus 1 minus 1. So here I've got 3 bits in the exponent. So 2 to the n minus 1 is 2 to the 2, 4, minus 1, 3. Okay? When I have 11 bits in the exponent, the bias, that shift, is going to be 2 to the 11 minus 1. So 2 to the 10, that's 1024, minus 1, 1023. We have an exponent bias of 1023. Okay? And then again, all zeros or all ones in the exponent have special meanings. All right, as far as the mantissa goes, okay, here we've got 4 bits for the mantissa. Again, we can always assume that the leading digit is a 1. In binary scientific notation, we can always assume that the leading digit's a 1, and so those 4 bits will just fill out spots after the binary place, okay? And so we're basically going to get 1 point something 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 times 2 to the exponent. Okay? So let's take a look at this. I've got 0, 1, 0, 1, 0, 1, 1, 1. All right? And so what number does this represent when we're using our mini float system? Okay? So we're going to break this out into the sign, the exponent, and the mantissa. Okay? So the sign is the first digit, or the first bit, which is 0. the exponent is the next 3, which is 1, 0, 1, and the mantissa is the last 4, 0, 1, 1, 1, okay? So I break it out into 0, then the next 3, 1, 0, 1, and the mantissa, 0, 1, 1, 1, okay? And so here, the exponent bits are 1, 0, 1, and so when I convert that into binary, I get 5, okay? 1, 0, 1 in binary is 5, right? Our exponent bias is 3, so this value actually represents 5 minus 3, or 2. So I have an exponent of 2. Is that okay? So 1, 0, 1, which is binary 5 with an bias of 3, becomes 2. All right? The mantissa bits are 0, 1, 1, 1. Okay, the last 4 are the mantissa, and those we plug into here. Okay, I got 1 point blank, 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 and so we fill that in with the mantissa bits, 1.0111. Okay, and I'm going to have that times 2 to the exponent, and the exponent, again, we determined was 2 back here, so it's going to be 1.0111 times 2 to the 2. All right, is this okay? All right, and so here, if I do this, and you could have done this anyway, so 1.0111 is going to be 1 plus 0 halves, 1 quarter, 1/8, 1/16 times 2 to the 2, or times 4. So if I just distribute the 4, I get 4 plus 0 plus 1 plus 1/2 plus 1/4, and this adds up to 5.75. Is that okay? All right, let's try going the other way. So here I want to represent the number 2.25 in binary with a mini float system, okay? So 2.25 represented in powers of 2 will be 2 plus 0 ones plus 0 halves plus 1 quarter, okay? So in binary, this 2.25 becomes 10.01. All right, is that all right with everyone? 10.01 for 2.25. Okay, and then so what I have to do is I have to turn this into binary scientific, right? So what do I have to do into binary scientific? I would take this decimal place and I would just roll it over 1, right? One position. So I get 1.001, okay? So I get 1.001, and because I rolled it over 1 position, it's going to be times 2 to the 1. All right, and so now I'm going to take this, now that I have binary scientific notation, I'm going to turn this into kind of our mini float system, okay? So I got 1.001 times 2 to the 1, okay? It's positive, so the sign bit's going to be 0, okay? The mantissa part is the thing that trails the leading 1, so I have 0.001, and so the mantissa bits, I need 4 of them, will be a 001, and then I just tack on a 0 so that we have 4 bits, right? So we can always add additional zeros after the final thing, right? We can always have trailing zeros, right? Like 3.5 is equal to 3.5000, right? So this is 1.0010, or 1.0010, right? So it's equal to that. So I have 0010 for the mantissa, right? All right, and so the exponent, what do I have? My exponent has a value of 1. So what does that become after the bias, right? So the exponent value is 1. So with the bias, we're going to get 4 in binary, okay? So 4 in binary is 100. Okay, I have 1, 4, 0, 2, 0, 0, 0 ones. Okay, so 4 in binary is 100. Okay, and so the number in binary becomes 0 for the sign, 100 for the exponent, and then 0010 for the mantissa. Okay, all right. We are going to continue expanding on this, talking about the special cases where we have all zeros or all ones in the exponent, and then there's some interesting other implications that that results from this. Okay, it's just like how do you even count in binary and stuff, and what happens there. And we'll continue that on Friday. Okay. So good luck as you guys study, and we will see you guys on Wednesday for the midterm exam, and we'll see you then. Okay.